Okay, in this example, we're evaluating a line integral for work where the vector field f of xy equals y cubed plus 1I plus 3xy squared plus 1j, and the path is a semicircular path from the point 0, 0 to the point 2, 0. Now we have a few options for solving this. The first would be to evaluate the line integral using the parametrization for that C1. And number two, if it is conservative, we'd have to check that first. We can use the fundamental theorem of line integrals and evaluate the potential function at the end and the start point. And also, if it is conservative, we could take a different path. But the last two options really do depend on if the vector field is conservative. So if we don't know right away if the vector field is conservative, we can go ahead and try that first option. Let's evaluate a line integral using a parametrization for C1. Now this is a semicircular path using some trig functions. We can find that if we use r of t equals 1 minus cosine ti plus sine tj, where the time intervals from 0 to pi, this actually would give us that path. And that's using conversion equation, knowing that it's part of a circle. And then to find the line integral for work, you need to calculate r prime of t, taking the derivative of 1 minus cosine t to get sine t, and the derivative of sine t to get cosine t. And this is your derivative function. Now you will have to replace all of the x's and y's in the vector field with x equals 1 minus cosine t and y equals sine t. So if you make those substitutions, and then you find the dot product, this is the integral that you end up with. The integral from 0 to pi of this entire quantity dt. Okay, this integral should dampen your enthusiasm for this option. This does not look like an easy function to evaluate, a definite integral to evaluate. Even using a calculator, it would be quite tedious to work through all those calculations. So perhaps we should check to see if the vector field is conservative, so we can either use the fundamental theorem of line integrals or take a different path altogether. So the second option, if it's conservative, let's evaluate the potential function at the endpoint and the start point. To test if it's conservative, this is your m, y cubed plus 1, and n is 3xy squared plus 1. You take the partial of n with respect to x, 3y squared, and the partial of m with respect to y, also 3y squared. So we can check if it's conservative, and if it is conservative, we're going to take the antiderivative of this m with respect to x and n with respect to y. Okay, so we do verify that it is conservative, and then finding the potential function, we can find that the potential function is xy cubed plus x plus y plus k. Again, you can go back to a previous section and practice how to get that potential function. And then using that fundamental theorem of line integrals, evaluate this potential function at the endpoint, which was located at 2, 0, and the start point located at 0, 0. And you'll find that the line integral for work is equal to 2. That's using the fundamental theorem of line integrals. Now the other option, since we've already tested it was the vector field is conservative, we can take a different path. In fact, this path C2 is a straight path with parametrization Ti. X equals t, y equals 0, and the time interval would be from 0 to 2. All right, so that's our parametrization would be ti. You want to take the derivative of that, which would just be 1I, and you would replace the x and y in the vector field with the original x in your parametrization. And this ends up simplifying to the definite integral from 0 to 1 of 0 to 2 of 1 dt. And when you evaluate it, you get 2. Of the three options, obviously the third one is the easiest. So this illustrates different techniques that you can use to evaluate a line integral moving from a start point to an end point. If the field is conservative, you've got more options. The English physicist Michael Faraday wrote, "Nowhere is there a pure creation or production of power without a corresponding exhaustion of something to supply it." This statement represents the first formulation of one of the most important laws of physics, the law of conservation of energy. In modern terminology, the law is stated as follows: in a conservative force field, the sum of the potential and the kinetic energies of an object remains constant from point to point.